Today we're going to look at how light reflects. As a quick reminder, light is really fast. It travels at 3 times 10 to the 8th meters per second. And as a reminder, when I say light, I am referring to all electromagnetic waves. It is independent, does not require a medium. As I mentioned before, it is not just visible light. And then finally, it does obey the law of reflection, which we learned about with mechanical waves. And that's going to be our focus today. This slide should look familiar as we looked at something like this with mechanical waves. We said if we have a ray that comes into a boundary, it reflects. And the angle that the ray reflects, or that comes in at, with respect to a normal, is equal to the angle at which a ray reflects at with respect to the normal. And a normal, again, is a line that is drawn at a 90-degree angle with respect to the boundary, or in other words, perpendicular to, in this case, the mirror. Objects can be considered specular or diffuse. And a specular reflector is like glass. It's going to be shiny and polished. And of course, it's going to obey the law of reflection. It's sort of like if you have someone that's standing right here and then the light coming off of them reflects to a friend, they can see them. But if you go a little bit off to the side, you might not be able to see your friend's reflection anymore. Paper also reflects light. If you take light on a piece of paper, it's obviously reflecting or you wouldn't see the piece of paper. But when it does reflect, it reflects the rays in all different directions. Now, even though it seems weird and it doesn't look like it, that is actually obeying the law of reflection. So if I were to draw what would a specular reflector would look like, I'm sorry, a diffuse reflector, not specular, it's not very smooth. And so if I were to draw a bunch of lines, a bunch of rays that are coming in, and then I were to draw the normal at each of those points, so this would be perpendicular, this would be perpendicular, that would be perpendicular, and, that would be perpendicular. And so if I were to draw the reflected rays, I'd get ones that are going in this direction, one that's going in this direction, one that's going in this direction, one that's going back in this direction, and so they would be going in all different directions, which is helpful because then you can actually see the light coming off of a piece of paper from any direction. You don't have to be in a certain spot. Like I could be right here and I could see light coming off a paper. I could be way over here and we see light coming off a piece of paper. But with mirrors, if you want to see something in the mirror, you have to be in very limited spots. Now, light comes off of objects, whether it's your own light that's being given off or light that's been reflected off of them, have two different words. If you're giving off your own light, such as the sun gives off its own light, candle, fire, that's considered to be luminous. And if light is coming off of you because it's been reflected off of you, well, then that's called illuminated. When we look at reflected light from an object, we talk about that light as being in our line of sight. And this is a line of sight right here. It's basically light that's coming off of this object, hitting the glass, coming to my eye. So this is the line of sight. Now the thing is, my eyes and my brain together cannot possibly interpret and understand how light could change its path, like here. And so what happens is we have light that's coming to our eyes from the mirror straight at us, and we interpret it as if that light originated from behind the mirror. And so the image, what you're seeing in the mirror, always looks like it's behind the mirror. So if you look at yourself in the mirror, your image, which I would describe as like your twin, is behind the mirror. Now, if I were to take a look at myself in the mirror right now, I would notice that my twin, my image, looks pretty identical to me. We're the same height, we're standing the same distance from that mirror, but there is one thing that's different. If I were to raise my hand, my right hand, let's say, and wave at the mirror, my twin, or my image, would wave her left hand back at me. So the only thing that's different about images with smooth, flat surface mirrors, called planar mirrors, the only thing that's different about them is the orientation. It's backwards. And if you've ever noticed, if you've ever pulled up in front of an ambulance before and you've stood and looked at the ambulance, the word ambulance is written backwards. And the reason for that is that if it approaches you and you see it in the rearview mirror, then the reflection would flip it around and you'd see the word ambulance written in the right orientation. So now let's specifically look at how light does reflect to make an image. Imagine you have a candle. Now the top part of the candle is luminous, it's giving off its own light, and the bottom part of the candle is illuminated. Light is reflecting off of it. Either way, there are millions of light rays coming off the top of the candle in all directions, so everybody can see this candle. And there are millions of light rays coming off the bottom of the candle, and there's millions of light rays coming off the middle of the candle. One of the light rays that's coming off of the top of the candle might perhaps hit a mirror. And then it obeys the law of reflection, and then may go to somebody's eyes. Well, again, that person gets light from the top of a candle coming and following that path, and that person interprets this light coming to their eye as having originated back here. So they see the top of the candle being behind the mirror. And likewise, the bottom of the candle, some of the light is coming off, hitting the mirror, reflecting to the person's eye, and they interpret it as if that light from the bottom of the candle is originating from here. So if we know where the bottom of the candle originates and the top of the candle, then we can put it all together and say, well, that's the image of our candle, and that's what we see in the mirror. Let's describe an image formed by an object in a planar mirror. So this is my object. It's the letter P. Light is coming off the object, hitting the mirror, and reflecting. Now, if someone were to observe the reflected light, they would interpret an image as being behind the mirror. Let's describe the image. First of all, the image is the same size as the object. It's also reverse orientation, which means it's backwards, the word ambulance. Where is it located? Well, the image is as far behind the mirror as the object is in front. So now you're going to start the reflection lab. My recommendation is that you pause this video and you watch the video where I demonstrate how to do the lab. And then you can come back to this video and finish watching. So now that you've gone back and watched the video, this is sort of a top view of the mirror, and you can clearly see that the line that I have drawn is the back of the mirror. And what you'll do is you will line up so there's this pin that's right here, and that pin is going to be giving off light. And some of those light rays are going to hit the mirror and they're going to come to wherever your eye is. So what you've decided to do is you've put these pins right in your line of sight. And you've done it on both sides. Maybe I'll make this one a little farther. Okay, and once you're done, you can take the pins out, you can take the mirror out, you'll be left with some holes in your paper and a line. And you're going to use your ruler and you're going to draw a line that's a very straight line that connects the holes to the mirror, and you're going to do the same thing on the other side. And then what you're going to do is you're going to connect back to the original object, which was the pin. This here. You're going to show that the law of reflection was obeyed on both sides. So you'll draw a normal, so, and you'll draw a normal like so. Then you'll take your rulers and you'll measure this angle and this angle, and they should be the same. And then you'll measure this angle and you'll measure this angle, and they should be the same. As far as which is the angle of incidence and which is the angle of reflection, well, this is the object right here. It's a pin. It's a pin with a tiny little piece of tape on it so that we know that that's the object. Light is coming off of the pin, hitting the mirror, and coming to your eyes. So really, this angle here is going to be your angle of incidence, and this is going to be your angle of reflection. And likewise on the other side, light comes off the pin, hits the mirror, reflects to your eyeball, and so we have that this is the angle of incidence, and this is an angle of reflection. What I do know is that the angle of incidence here has to be equal to the angle of reflection, so you will draw them, measure them, and if they are the same, just label them. If they are not the same, you're going to have to write a little asterisk saying, I understand these should be the same to get full credit. And then do the same thing on this side. Angle of incidence has to be equal to the angle of reflection. Now, these pair of angles do not have to be equal to the pair of angles over here. All right, your next step is then to trace your line of sights backwards. But I would ask that you draw dotted lines when you're behind the mirror, because no real light is getting behind the mirror coming from the pin. And then you do the same thing on the other side. Where those two lines cross, that's where you have your image. So you'll be drawing all this on the pink piece of paper. Your final step is going to be to measure the distance. So I want to know, what is the distance from your image to the mirror, and what is the distance from your object to the mirror? Those should be the same. On my rough sketch, obviously it's really bad, but yours should be the same. And again, if it's not the same, just write a little asterisk saying, I know that these two should be the same for full credit. The video goes through this as well, but just another little added piece. Here there's a marker, and in front of this marker is a pin, and that pin has a tiny little piece of Scotch tape just to help you identify that that's the pin we're looking at. Now this right here, this is the image of the pin. You will take pins on your side of the mirror and try to place them in the line of sight with the image. So here I've taken a pin and I've put it in a piece of paper. And the line that I'm looking at right now, this is definitely not behind or blocking this image. So I'd either have to move the pin over, or I'd have to adjust my line by moving my head until your pin does directly line up. You can kind of see that transparent tape there. So when this pin is lined up in front of that image, then you've done it. But it does take more than one pin to make a line. So now what I'm going to do is I'm going to add my second pin. Here clearly is not a good example. This real pin is not lined up behind this real pin. I can see that the image is lined up behind one of them, but certainly not both. Here you can see that there's one pin, and you can kind of see the top of the next pin, and then you can see the other pin. So they're all in a line there. When it's all said and done, you should be able to identify where the image is. And once you've figured out, you can see here there's some lines. Once you've figured out where the image is behind, you can take a marker, your second marker, and you can put it right where you think the image is, and it looks like here's the image of the marker, and then here's where I put the real marker. It looks like all one thing, if I've done it correctly.